and this can come up in a whole lot of different ways. So what I've chosen to do is go over one NCQA question, but basically the data be given and we'll be asked how well it fits a certain model, usually working from a graph. So we can look at the distribution. So this one is toilet data, curiously. The data is based on a study of New Zealand households and how many times the toilet is flushed. So there's two things shown. The data, the experimental distribution is in the bar. So these are the measurements. So about a quarter of the houses had 4 flushes during a 24-hour period. A wee few had 10. What's shown in the bars is what a Poisson distribution would look like if the average number of flushes was 4.7. And so we're asked to decide what's going on. Does it fit? And so this is the wording of the question. Discuss 2 reasons why that may not be a good model. Now, the thing I think is to look at 2 things. The context and consider, and compare some actual probabilities. So we're looking at a 2-pronged approach to this. Are there conditions for the Poisson that just aren't practical here? And can we compare some actual probabilities? So you have to know those conditions for the Poisson, the normal, and the binomial. You have to have them fairly clear in your head to be able to answer these questions intelligently. I'll just quickly look at the mark scheme. So 2 reasons fully discussed using context and the data and the model. So possible reasons why the Poisson model is not. You would expect a person to flush the toilet more than once a day, but in the model predicts that 5.2% will use it only once. So there, yeah, you see the model here predicts that, but we would expect that people would be using the toilet at least a couple of times during the day, and hopefully for the rest of the people in the household, flushing. Okay, the model predicts roughly 19% of the people will flush the toilet 4 times a day, but 26 of the people flush the toilet 4 times a day. That's 8% is different. So here we go. 26% people did, and if we use the Poisson distribution to predict, it would way under predict that maximum value. It predicted at about 19 or 18.5. And so here we're comparing what was observed in the data set and what would be expected in the model. Sometimes you've got to use your calculator to calculate that value, so the bars may not be provided and you would go into Poisson and work that out. But you would work them out and mark them on, so they've done some of the work for you. So we're looking at a contextual one first. Surely people would be flushing the toilet a couple of times or more. It seems odd to predict these 2 things here. So the Poisson model doesn't allow for the context. Secondly, an actual probability issue. In practice, we found 26%. The Poisson model would be way under that and miss the point, so that's 2. Sometimes a person needs to flush more than once to complete the job, so the event of each flush might not be independent, and you could go on and that there could be an illness in the house that had the impact on, one person's flushing may, if they're unwell, may lead to more, that sort of thing. Not a good topic, but what is interesting is we've got a contextual issue here. We've got another contextual issue here dealing with the idea of independence, which is one of the conditions. So we've looked at, and in the middle, we've got a calculation-based difference. If I use the Poisson model, it's saying 19%. I'm seeing in the actual data 26. That's a significant difference. So I've listed here 3 reasons. This would never be an exhaustive list, as it says. except any other valid reasons.